Really quickly, there's not much to say on my who slide. My name's Haroon. I work for a tiny company in South Africa called Thinkst. The main takeaway for you guys for that is I flew about 30 hours to get here, which is why my voice is hoarse, not because of anything that happened last night. I promise. So really quickly, one of the questions is why I bothered with this talk. And a little while back, Halva, if you're at Black Hat, you probably know Halva's name. Halva tweeted saying, can someone write a history of code exec from 95 to 2009? Okay, and this topic comes up periodically, and some guys have done some work on it. Ben Hawkes did some work on it at an Australian conference. A long time ago, Ben Nagy released a paper at EI with some of this information. But a few years ago, a big discussion broke out because someone in academia released a paper and introduced a topic called return-oriented programming, and the world basically crashed because everyone who wasn't in academia screamed that academia was stealing it. Academia screamed that these pesky hackers never give attribution for anything. What do they know anyway? And so it kind of became big news. Recently, Nico Weissman from ImmunitySec basically said the same thing again. Every time you heap spray, someone thinks he just pioneered a new technique that somebody else invented in the 90s. Okay, so basically with this talk, what I'm saying is Twitter made me do it. Okay, the Twitters convinced me that somebody should try to put all of this stuff together in one coherent talk or paper. One of the hidden reasons that I've got is to demystify part of the stuff that's kind of mystical. And while that sounds grand, my aims are simpler. Back in 2003, for example, there were lots of us saying, we can do that simple stack stuff, but once you get to heap stuff, that stuff's crazy voodoo, okay? And today, if you give someone a chance for a safe heap unlink 4, they kind of look at it and go, hey, that's easy stuff, it's the new stuff that's crazy. And so in part, when it comes to memory corruption attacks, there's a barrier to entry that stops people from fiddling. And once you're over that barrier to entry, lots of times you discover that you've got a knack for it, and people go on to do some coolness. So I'm hoping to kill some of that. And the bottom one is simple. Solar Designer clearly wasn't human. And I think it's wrong for anyone to call him human. So one of the things I did with this talk is I ended up collecting a whole bunch of data. And as a geek, the moment you collect a bunch of data, the first thing you want to do is graph it. So I graphed a whole bunch of stuff, and most of it adds absolutely no value. What you're seeing up there is simply how many talks at Black Hat covered stack exploitation or heap exploitation in the last few years. Okay, so clearly it's been a huge topic of concern. But in truth, again, the main reason for doing this talk is because Mark Dowd pointed out that chicks dig memory corruption bugs. Okay, so really quickly, I'm going to give you some caveats on the talk. I had an intention, which was to start collecting this data. The task is too big for one guy, so I need more people to jump in. And so I kind of set arbitrary limits so that I could present something, and I'm hoping that after that it kind of takes on a life on its own. So one of the first things that I did is I chose to focus only on x86, only on Microsoft, only on Windows. Now, of course, this cuts out a whole bunch of innovation. Okay, it cuts out all of the stuff that FX did on Cisco iOS exploitation. It cuts out stuff that John McDonnell did on Spark. And some of those are really bad because the exploitation that they did informs the exploitation on x86. Okay, so you'll see, we'll come to it, but lots of the ROP stuff that gets discussed today was kind of done by John McDonnell on Spark a really long time ago. Also someone whose humanity is slightly in question. But so for this talk, we kind of focus on x86. The other one of the guys who read the paper earlier pointed out that my view is myopic, okay, which means essentially I've got a very Western view of things. And this is largely because of my own inability to read Chinese websites or read websites that don't have English on it. Google Translate's not that helpful for this stuff. There's probably a wealth of information in languages that I don't understand. And periodically, we see this stuff pop up. So the first SEH overwrite attack that we see coming out happened in a worm that was written by someone in China. And we didn't see that attack happening for a while. But so I'll miss that stuff. If you know that stuff, if you know people who know that stuff, go to the timeline, edit it in. It's going to be useful. This is my only lolcat in the whole talk, I promise. My point here is really simple. If you try to calculate how many hours we're trying to compress into this talk, you're looking at something like 300,000 into a 1 hour talk, which means it's going to be lossy. Every one of the techniques that we talk about deserves a black hat talk on its own. We're trying to do all of them in 1 hour. You're probably going to lose some information along the way. Disclosure, bugs, and counts. Everyone knows the R-Snake Taviso issue that happened recently. I'm not talking about that at all. What I do want to talk about, again, was another semi-pointless graph that I decided to put together. And this is one of those things when you're doing research like this that starts off like an okay idea and rapidly descends into a horrible idea as you do it more and more. So I started off saying, well, we've got OSVDB, which is a source of reported bugs. Why don't I just troll OSVDB and see how many bugs were memory corruption bugs? And so I pulled the DB and started doing some counting. And then you realize that the data needs some fixing up, so you start writing ugly bash scripts to fix it up. And eventually you've invested so much time doing it that you might as well just go all the way and do it. But what you end up with is a graph that looks something like that. And what we're looking at there in red, what you can see is memory corruption bugs as they reported, and the rest are total vulns reported. Okay, and there's a whole bunch you actually can read into this. The one thing that's interesting, Marco pointed out, is that memory corruption bugs are kind of plateauing, but they're not dipping. So while the total vulns went up and down, memory corruption bugs seem to kind of stabilize, but it doesn't mean that they're going away. The total vulns, of course, the extreme slope that you see there is because people started reporting XSS in Uncle Tom's PHP cart. So those bugs went way up. But what you notice from it is that memory corruption bugs aren't really going away. Okay, the numbers aren't dipping significantly. They still reported a lot. I've still got this data, and it's still worth playing with, because it would be interesting, for example, to isolate just certain vendors from it. So if you just looked at Microsoft, Adobe, and Apple, for example, I'm sure you'd lose the noise of Uncle Tom's PHP cart, and those graphs will actually look a lot worse. So quickly, the first timeline that I decided to do, so I said, okay, we're going to build this timeline and add all of the events that were important for memory corruption on this timeline. And I kind of started with the top of mind, like, okay, I know this happened. Let's Google and find out when it happened. And clearly, this approach is incredibly naive. Okay, so there's just too much of data, and you miss a ton. And so what we ended up doing is, if you go to that URL up there, which is a bit of a mouthful, I'll fix it and shorten it after the talk. But basically, this timeline gives you an interactive way of graphing the events as they happened. I don't have internet access here, so I can't really show it to you. But what's interesting is, for each of those items that you click on, you then get more information on that event. Okay, and you get information, you get links to more information, links to documents, and there's a few feature requests that I'll discuss in a little while. None of that stuff is actually difficult work. It was done largely because of a project that MIT have to build interactive timelines. It's literally something that took like half a day to put together. Right now, there's no authentication on it, and I don't plan to put authentication on it. So you can go there and decide that you know about this event that happened at a certain time at that event. People will look at it and alter it and argue about it. But if you feel something deserves to be there, go on, put it up. That information needs to be stored somewhere. On your CDs, you should have the paper that came out of all of this. The papers, so you've probably got a better chance of gaining useful information from the paper. If for no other reason, it's way unlikely that we're going to finish all of the content during this talk. But you can pick that paper. It should be on our website when we're done. So at the end of this talk, you're not suddenly going to be able to exploit stuff left, right, and center. Okay, but what you should know is when someone says, well, that's an unlinked 4-byte write anywhere primitive, you should have an understanding of what that means. And you should be able to say, well, that used to work before, but stopped working because of the following reasons. Okay, so the first question becomes, where did all of this start? And in truth, it started a really, really long time ago. So John von Neumann was a mathematician born in 1903. Okay, and largely the machine architecture that we use today, von Neumann architecture, is the one that's on the top right there. And essentially von Neumann architecture uses the same hardware for instructions and data. Okay, so there are alternative architectures, notably the Harvard architecture that's down there, that separates instructions from data. But a lot of the memory corruption problems that we see come because we use von Neumann architecture. Okay, so the question becomes, really quickly, we needed to do a graph on memory basics, and we figured that all elite memory explanations should be done in ASCII text. Okay, I kid. So memory, if you look at it really quickly, and I'll blitz through some of this. So basically, every process on your machine thinks it gets 4 gigs of RAM. This stuff looks up on a page table to actual physical RAM. And the kernel gets mapped in at the same location. So the kernel runs it, and everything running thinks it gets its 4 gigs. This memory is further segmented. So there's segments in there, text, data, heap, MMAC. Different OSs will do this slightly differently, but essentially you're looking at region of memory to store your code, region of memory for shared libraries, region of memory for the stack, region of memory for the heap. Okay, and we'll discuss why this stuff becomes important. So one of the questions is, what is code? Okay, on your machine, what you're looking at there is just a random hex dump of some running process. And if we look at that stuff, okay, the question is, what is that stuff? Okay, and in this instance, the instruction pointer looks at it and says, that stuff's code. Okay, and so it executes, if the instruction pointer got there, it would execute these commands. Okay, and the problem is, if you looked at this, which looks like instructions also, and you looked at it in the dump, you can't tell that actually that's just data. Okay, so that's just a string. And again, this comes back to the problem of using von Neumann machines. Okay, data can be instructions, and instructions can be data. Okay, and this is a problem that we're carrying around for a bit. So really quickly, I'm going to add another caveat. Last year, we did a talk on hacking cloud stuff, and we ended up trying to do like 100 slides in the hour that we had. So this year, I've only got 38 slides, so we should hopefully make it. But instead, I've decided to try something new, which is Prezi, which has something like 160 slides, which might explain why I'm talking really quickly. So the point of this talk, again, is to examine that timeline of events as they happened, and we'll try to take them almost completely from the beginning. Okay, so one of the things that should surprise you is the first documentation of memory corruption attacks actually happened in 1972. Okay, there was work done for the US Air Force that basically documented stack smashing. It went into detail in several locations saying this is what happens, parameters are not checked, you get to overwrite a return address, bad stuff will happen. Okay, the really important thing to note there is that date. It's literally before I was born. Marker's a different story. So I'm going to blitz through. FRAC 1 was published. When FRAC was originally published, it was a freaking magazine. But because so many interesting things get documented in FRAC over the next quarter century, the starting of FRAC at least deserves a mention. So Taran King, Night Lightning set it up, and it actually becomes valuable. In 1988,